Good morning, everyone. Today what we're going to be looking at is we're going to be looking at some more differentiation by rule, but this time we're going to be working with some negative powers. So what I've got here is an example, and it's kind of deep because it's got lots of different steps. So what we need to do is we need to do something with this first before that we can differentiate it. Now what I've got here is a long weird function, but it has a restriction on it. X can't be 0, because if x is 0, then I have a divide by 0 error. But I can still differentiate it by breaking it into its individual parts. So y equals x squared over x cubed minus x over x cubed plus 3 over x cubed. Now, using your index laws, these first two should simplify down very easily. Remember, when you are dividing an indice by another indice of the same base, you subtract the powers. So that leaves you with y equals x to the 2 minus 3, which is minus 1. This one here is x to the 1 divided by x to the 3. So that's going to become x to the minus 2. And now the last one, we have to refer back to our rule at the top of the page. A to the negative n is the same as 1 on a to the n. In this case here, a is x and n is 3. So I'm going to have it as plus 3x to the minus 3. Now, I have to always remember that x can't be 0. That's just a fact of life. X can never be 0. So now that I have my equation looking like that, it is in index form, it's got powers, I can now differentiate this via rule. I do it the same way that I've done all my others. So dy dx is equals to negative 1x minus 2. Minus 2 comes down and becomes plus 2x, subtract 1 from the power, minus 3 times plus 3 is minus 9, x to the minus 4. Again, x can't be 0. Alright, if any of these sort of things, if there's a restriction up here, the restriction will keep applying as we go down. And then if you were to write it in a similar way to how it was written at the top, you could write it as negative 1 on x squared plus 2 on x cubed minus 9 on x to the 4. But if you wanted to write it as a singular fraction, what would I have to do? How could I express, again, x can't be 0. How would I express all of that as one fraction? I need to do the opposite of what I did up here. So I took that and I split it apart into thirds, then cancelled down. I now need to make this and this have an x to the 4 on the bottom. And I can do that by multiplying this one by x squared over x squared, and then this one by x over x. So now I have negative x squared over x to the 4 plus 2x over x to the 4 minus 9 over x to the 4. Again, x can't be 0. And the final answer is going to be negative x squared plus 2x minus 9, all divided by x to the 4, and x can't be 0. Think about this in terms of varying degrees of correctness. This is still correct. This is the most correct. Sometimes you are going to see questions where they ask you to express your answer in a particular form. They might say, express your form in, AXN plus 2n. They'll ask you, and they'll write it out, and they'll want you to write it as using only positive indices. And that's where you go from here to here, being this isn't correct, but this is, because they've asked for a question in a particular answer to a question in a particular form. And that is when you have to do the extra calisthenics to get your equation to look like the one you had at the start. It's similar to how sometimes the questions will ask for, provide your answer in, a plus root b or something, where they want the square root involved. It's the same as when I turn around and ask for, when I say and I ask for something to be in exact values. All right, so if we look at, if we go and we look at x to the minus 2, 2x to the minus 1, plus 3x. All right, so this one's a little simpler because there's no fractions, there's no calisthenics to be done. X to the minus 2. Minus 2 comes down, so this is just y. So we're doing dy dx. Minus 2, x to the minus 3. Minus 1 comes down. And then plus 3 on the end. All right. The rules still apply, but you have to make sure that you're taking your powers down properly, and that you're making sure that the negative comes with it. Because you can see here, between here and here, that negative 1 falls down. So that plus 2 now becomes minus 2 because that negative 1 there. All right, you got to make sure that you keep paying attention to that, and you keep that going. All right, and if you wanted to just be extra careful and only write it using positive indices, now in most of these cases, yes, obviously x can't be 0 because you're going to introduce a divide by 0 error. So take that as a given. So I'll give you one more example. And this time it's going to be going to be more like an application task, because what I'm going to ask you to do is I'm going to ask you to find the tangent to f of x at f of 3. F of x is equal to, I'll be nice. -1 on x squared plus 2 on x. Again, x can't be 0. All right, I'm going to give you a moment to think about that. There's a lot to unpack in this question. First things first, to do a tangent, that's going to be a straight line. All right, so it's tangent with a straight line. And to do the straight line, I need a second point. So before I go and do anything else, I need to actually figure out what is f of 3. So that is -1 on 9 plus 2 over 3. Now 2 over 3 happens to be 6 over 9. So I just multiply all the numbers by 3. So that means I have -1 over 9 plus 6 over 9, which becomes 5 over 9. So that means that the coordinates that we are going to need to be using for our final tangent are going to be bracket 3, 5 over 9. So we need to keep that in the back of our minds. We've got that we've got to work with. So now we have to handle the other part. To do a tangent, we need two things. We need a point that it passes through, and we need the gradient at that point. So to find the gradient, we need to find f dash x. So in this case, f dash x equals, so in this case here, before I do f dash x, I'm going to reorganize f of x just a little bit so that it is in negative, so it's using indices form properly. So that's going to be negative x to the -2 plus 2x to the -1. So I've taken these, put them into the negative power form. Remember, 1 on a to the n is the same as a to the -n. And now I can find f dash x. -2 comes down, minus and a minus becomes a plus, so it's going to be 2x to the -3 plus 2x to the -1. -1 comes down. So that plus will be a minus, x to the -2. So I will quickly reorganize that back to something that we can work with in terms of fractions, make our lives a lot easier. So that's going to be 2 over x cubed minus 2 over x squared. Now that I have this here, again, x can't be 0, we can now find f dash 3. Okay, if we've got f dash 3, then we can keep going. So, that's going to be 2 on 3 cubed minus 2 on 3 squared. 3 cubed is 3 times 3 times 3, which is 27. That's going to be 2 on 27 minus 2 on 9. Now the 9, 2 over 9, can be turned into the 27 by timesing by 3. And that means that it becomes 6 over 27. That means that my final answer for the gradient at f-3, so the f-3 is equal to 2 over 27 minus 6 over 27. So that answer is going to be minus 4 over 27. So now I have a gradient, and then I have 3 and 5 over 9 above. And 3, 5 over 9. Formula for finding the tangent is the same as the formula for finding a straight line with a gradient and any single point. Y minus y1 equals m x minus x1. So I'm going to put my y minus 5 over 9 in there, equals minus 4 over 27, bracket x minus 3. Now I can already see that I'm going to need to do something with this 27 and this 9. So before I do any mucking around with expansions, I'm going to quickly change this 5 over 9 to 15 over 27. All right? Because I know that whatever I need to do is going to involve converting that 27. So 5 goes to 15 because 9 goes to 27. So that's times 3 on top and bottom. I'm now going to expand this into here. So I have y minus 15 over 27 equals minus 4x over 27. Minus times a minus is a plus. So it's going to be plus 12 over 27. I'm now going to add 15 over 27 to both sides. Y equals negative 4x over 27 plus 12 over 27 plus 15 over 27. That looks awfully convenient. What's 12 plus 15? It's 27 as well. So what's 27 over 27? It's 1. So my final answer actually comes out to be negative 4x over 27 plus 1. Smiley face. So the equation of the tangent at f of 3 f of 3 is minus 4x over 27 plus 1. And remember, your CAS can help you with this. Why did we sub in 3? So the reason why we had to sub in 3 is because we needed the gradient at 3. Because remember, the tangent is a line that when it passes through the original equation, it passes through at exactly that point. It doesn't pass through at 3.01 or 3.02 or 2.99. By making the tangent equation have the same gradient at f of 3, we can make sure that we have a line that only passes through at that one point. They just touch and then they go away. They don't touch again. So, for reference, let's bring up our CAS. There's my CAS there. So I'm going to just quickly do ddx minus 1 on x squared plus 2 on x. Just to make sure that I've got my fractions all lined up. Otherwise it might get a little confused. All right, cool. So we've got that. All right, so give me a sec. I'll just move the CAS into a good position for you all. So there's the answer there. There's my answer there. Now they are the same, except what the CAS has done is it's simplified it down to just a simple one fraction as opposed to a spread out. So from there, to use our CAS to make sure that we've got the right answer. So what I'm going to do is I'm just going to quickly define f of x equals my function. Drag that down. So now when I do f of 3, it gives me 5 over 9. So cool, I know I'm on the right track. I know my answer's correct so far. And now I have ddx of f of x, which is still that. I can now, what I'm going to do is I'm going to go back up and I'm going to define it so that g of x is always the derivative of f of x. And this works for all the other derivative questions that you might do. So defining g of x as being the derivative of f of x means that when I type in g of 3, it now just straight away spits out the derivative. It finds the derivative of f of x and then substitutes in the value that I want. All right, so now what I've got, and then I can set up in here and I can go y minus y1 equals and it solves it for me. Oh no, you're allowed your CAS for this set because it'll be an applications task and you'll be doing a lot of this sort of stuff anyway. Surprise! So what I've got in here is y minus y1. I've got m written there, the minus 4 over 27, and then I've got the x over 3. So to make it a little clearer so that you guys can see where the fraction is, there's the 27 there. And if I hit enter on it, the answer still doesn't change. All right. So all right, so I'll do quickly one more on the CAS. But I'll do it entirely on the CAS. Let's go y equals 3 over x squared plus 4 over x cubed plus 2 over x. So this is the new equation that we're going to be working with. Alright, so there's our new equation. So we're going to go in and we're going to enter this into our CAS. So I'm going to, and then, I suppose you guys figured need a point to work with. So I want to find the tangent at x equals 1. Alright, so I want the tangent at x equals 1. Okay? Tangent at x equals 1. So on the CAS, let's clear all variables. Clear all. We don't want to accidentally have any of the old stuff in our calculator memory causing us to make a mistake. So first things first, we need to define our function. So define is found under Math 3. And then define f of x. And you can enter this in with as much of the formatting as you like. It will be able to handle it. So I've got, so if I just type in f of x, it spits it out for me, and it puts everything in to itself a logical order. So you guys can see that there. And then what I'm going to do is, just so that I have it handy, I need to know what the value of y is at x equals 1. So I'm going to search for f of 1, and that's 9. So I have 2 pieces of information. I have the function, and I also know that it will pass through the point 1, 9. Now, back on the CAS, we're going to define a new statement. We're going to define g of x is equal to, under math 2, d dx, and then we're just going to type in f of x. Hit enter, and then we're going to ask it for g of x. Now, it is going to give it to you in this form, as opposed to how you would do it if you were doing it by hand. Both answers are correct, but remember, at the end of the day, what I care about is the equation of the tangent. Okay? What I care about is the equation of the tangent. So if you were to simply state f dash x is that, whatever's on the CAS, that is acceptable. Because at the end of the day, what we really want is g of 1. So what I now have is I have the coordinates at x equals 1, and I now have the gradient at the point x equals 1. So from that, I can now do my formula. Y minus y1 equals m bracket x minus x1. I know that m is minus 20. I know that x1 is just 1. And I know that y1 is 9. And then from there, a simple case of expansion and rearranging. Y minus 9 equals minus 20x plus 20, plus 9 to both sides. Y equals minus 20x plus 29. All right. And that is my final equation. So the tangent equation, tangent at x equals 1 is there. The cool thing we can also do with our CAS is, because we've defined the functions, I can just draw, I'm going to ask it to draw f of x. And then I can go analysis, sketch, tangent, and I can type in x equals 1. I can hit enter, and it will tell me the answer. The equation of the tangent is minus 20x plus 29. And it even tells me where the point is. It's at point 1, 9. In response to your statement that the CAS is magical, it's only as magical as the person who is using it. Right? The CAS is only as capable as the person is at using it. All right? So I would like you guys to please do 17C. But there are some questions in there that I do not want you to do, because it's asking you to do this with first principles. Don't do that. That way lies madness. I mean, you can if you want. I'm not going to stop you. But if you look at questions 1 and 2 and go, nah, no, don't worry about it. Okay? The questions I really want you to do from 17C are 3, 4, 5, and 7. Okay? So 17C, questions 3, 4, 5, and 7. They are directly linked to the work that we have just gone through and practiced. All right? So the work that we have just done, is directly applicable to those questions. All right, so recording is